Hello everyone, and welcome to today's chem lesson. Today we are going to continue our discussion about solutions by taking an old concept and applying it to a new situation. We know that we need everything in chemistry to have a different name. Right? We've seen this before when we talked about naming. We've seen this before a couple of different places. Right? We need each thing in chemistry to be named something different. And so that means if I have 2 cups of water, let's look, there's 1 cup of water, there's another cup of water. And in this cup, I put a single grain of salt. Versus in this cup, I put a whole spoonful of salt. Both of these things are salt water. We don't really want that. The contact solution that you use to clean your contacts or store them in overnight, that's salt water. That's a saline solution. The ocean is salt water. Right? But those are 2 different things. We need a way to talk about solutions and classify them by how much stuff is in them. Right? I want to be able to look at the amount of stuff that goes into the water and say, okay, there's a little bit of salt in this water. There's a medium amount of salt in this water. There is a large amount of salt in this water. So that when I say salt water, I'm not just referring to any amount of salt. And that's where these 4 terms come in. These 4 terms, unsaturated, saturated, supersaturated, and saturated with extra, are going to help us determine how much salt is in our water. Right? These are easiest to see visually, so I went and I made little diagrams for us. Right, let's look at these 4 cups of water and the amount of ions, which we have as these orange things, right? All these ions that are floating around in the water. Our first solution here is an unsaturated solution. It is not holding the maximum amount of ions that it can hold. Plain and simple. Saturated, this second one, is holding the maximum amount of ions it can hold, the maximum amount of solute. I made these diagrams so I got to choose what saturated was. I chose 4 orange balls to be saturated. Any more than 4 and it can't hold it. Right? Any less than 4, right? So here we've got 2, but if it had 1, 2, or 3, that would be unsaturated. Here, exactly 4 is saturated. Supersaturated is when the solvent is holding more than the maximum amount of solute. Right, so that's anything greater than 4 in this situation. Now, I hear you saying, Mr. M, what's the point of having the maximum be 4 if it can hold more than 4? And the reason for this, right, the reason why supersaturated exists, isn't because I can do better than saturated, right? It's because there are some situations that allow for more solute to be dissolved. Right? These are normally very, very delicate solutions, right? Any stirring or moving it around will cause it to move over into our last category, saturated with extra. But there are plenty of solutions that are supersaturated. Right? Honey is a great example of a supersaturated solution. Honey is just sugar water. But there's so much sugar that it becomes its syrupy honey self. Our last category here, saturated with extra, is saturated, right? There's 4 dissolved things, right? 4 things floating around. But on the bottom, there's a pile of undissolved solid. Right? When we have saturated with extra, before you stir up your Kool-Aid or lemonade mix, right? You see the solid on the bottom. Right? If you finish stirring up your Kool-Aid or lemonade and there's still solid on the bottom, that is saturated with extra. The water is holding the maximum amount it can hold, but there's still some left over that can be dissolved if you make it supersaturated, or will trade places with the other ions that are down here. All right, let's take that salt water example from before and run it through. I have a cup of pure water, empty water, and I take salt and I slowly add salt. I start at unsaturated. I'm adding that salt, and the water is not holding the maximum amount of salt that it can hold. Right, we add salt, we add salt, we add salt, we add salt, until we are saturated. The water is holding the maximum amount of salt that it can hold. Then we have 2 options. Option A, we add more salt very slowly and very carefully, and the water becomes supersaturated, holding more salt than it should be able to hold. Or option B, we add salt super slowly, super carefully, and the water doesn't hold it, and that salt just settles down to the bottom here. But salt is different than sugar. Alright, I can do the same thing with sugar. I pour some sugar into the water, pour some sugar into the water, pour some sugar into the water. And we're running through these same steps, but sugar and salt aren't the same. Alright, the maximum amount of orange dissolved things for this amount of water is 4. But what about these little red ones? Right? What if I replace them with little red ones? Would that be 4 too? Or would it be more? Or would it be less? Again, just like when we talked about what is soluble and what is not soluble, this is not something that we just know. This is something that we use the reference table to help us with. And the piece of the reference table that helps us with deciding when something is saturated, unsaturated, or supersaturated is table G. Now, table G looks a lot more intimidating than it really is. Table G is a bunch of superimposed lines. At any given point, we're only really looking at one of these bold lines and pretending that the rest aren't there. Alright, so let's take HCl for example. Let me bold over this line. This is the line for HCl. Any value below the line is unsaturated. So that means all of this, any point down here, is unsaturated for HCl. So if I picked this point and I had 20 grams of HCl in water at 50 degrees Celsius, that would be unsaturated. The water could hold more HCl than that. Any value above the line is either supersaturated or saturated with extra. So that means all of these points above the line are saturated with extra or supersaturated. Now, Mr. M, how do we tell the difference between saturated and supersaturated and saturated with extra? And that's all in the description. If they're telling you about a solution that has no solid, but is above the line, that's supersaturated. If they're telling you about a solution that's above the line, but has solid at the bottom, that's saturated with extra. Lastly, any value on the line itself is saturated. So any of the points that are directly on the bold line. Right now, am I going to use HCl as this line every time? No. Right? If I was using HCl as the line every time, what's the point of having the rest of these lines on here? Depending on what the question is asking you, you're going to pick the line accordingly. Alright, now let's look at this example. Alright, I put an example on here for a reason. How much ammonium chloride would we need to saturate 100 milliliters of water at 70 degrees Celsius? Now, ammonium chloride is NH4Cl. So for this question, I'm going to be looking at the NH4Cl line. And so I'm going to bold that out, and I'm going to pretend the rest of these lines aren't here. Right, so I have one of my three things. I know my solute. The second thing that they give me that I need to know is my temperature, which they give me, 70 degrees Celsius. The third thing that I need to know is what they're looking for. Are they looking for saturated, unsaturated, supersaturated? And they tell me here, saturate. So I know that I'm looking for something that is directly on this line. And what they ask me, the fourth thing, is the amount of solute. Right, so they gave me the first three, and they asked me for this fourth. So I'm going to find the spot where this red line intersects at 70 degrees Celsius, and it's right here. And I'm going to follow that across to my y-axis with a semi-straight line and get 61 grams of NH4Cl. Now, I hear you. I hear you saying, but Mr. M, you underlined 100 milliliters of water and you didn't do anything with that. And that's a very good observation, right? They gave me 100 milliliters of water and acted like it was important. And it is. If we look at the scale of the y-axis here, it says grams of solute per 100 grams of water. that means that this scale, 0, 10, 20, 30, 40, 50, 60, 70, 80, all the way up to 150, this is how many grams of solute I can put in 100 grams of water. So they have to tell me the 100 so that I know that this scale doesn't change. If they told me a different number, right, if they said 200 milliliters of water, all of these numbers would then effectively double. Right, and instead of 61, my answer would end up being 122. If they gave me 50 milliliters of water, my numbers would essentially halve. So instead of 61, I would get 30 and a half. Because this proportion is for 100 milliliters or 100 grams of water. Now, really, those are the only two other options for amount of water that you will ever see, right? Sometimes they will say 50, sometimes they will say 200. And that just means you adjust accordingly. If 90 grams is for 100 grams of water, 90 grams would double for 200 grams of water and be 180. Right, these are all going to scale appropriately, either doubling when the water doubles or halving when the water halves. Let's take a look at another practice problem. At what temperature is a solution of 52 grams of HCl in 100 milliliters of water saturated? When we look at this question here, we are going to get 1 as our answer. Let's look at the pieces that they give us. They give us 52 grams, they give us HCl, they give us 100 milliliters of water, they give us saturated. Right. HCl means we're going to be looking at this line here, which I did a poor job. Right, we're looking at this line here. So that's HCl. 52 grams means we're going to be looking right around here. Right along that intersection. Saturated means we want it to be on the line. So that gives us where this 52 should meet, right, on the line. 100 milliliters of water means we use this scale as given. And then they ask me what temperature. So I follow this down to my 70 degrees Celsius. What about this one? You make a solution of ammonia. here, our correct answer is 2. And let's look at the pieces that they gave us. Right, they told us ammonia, which means we're looking at this line. They told us 50 grams of solute, 100 grams of water, which means we're using this as given. And they're asking us for the temperature and when it is saturated, so on the line. So we want on the line 50. And we want to know what temperature that lines up with. We're going to follow that straight down. Right in between 20 and 30, so definitely not 20, definitely not 30. In between gives us 25. Right, notice that they give you these pieces of information. They either give you the mass and the substance, or they give you the temperature and the substance, right, like we had last time, or they're going to give you the mass and the temperature and ask you to solve for it. Right here, be careful. Sodium nitrate is NaNO3. Is this saturated, yes or no? Here, the correct answer is no, it is not saturated. Let's break that down. Right, they give us sodium nitrate, which is right here. They tell us 35 degrees Celsius, which is right here. 100 grams of solute, which is right here. But then they give us 200 grams of solvent. "200 grams of solvent" means all of these numbers should be doubled. Right, so 100 isn't actually up here for 200 grams of solvent. 100 is actually down here for 200 grams of solvent. And when we follow this across to 35, we get this point, which is way under the line. So it is not saturated. Normally, 100 grams, right? If this was 100 grams of solvent, this would be a saturated solution, right? 100 and 100 at 35. But with the doubling of the water, right, we don't have 100 grams of solvent. We have 200 grams of solvent. So instead of, like I said before, if we double the water, all of these numbers get doubled as well. So this point is actually 200 grams. This point is actually 100 grams. This point is actually 40, 60, 80, because we have 200 grams of water. Right, like I said before too, if we had said 50, right, if this was 50 grams, then all of these would be cut in half as well. It would be 50, 25, 20, 15, 10, etc. Right, whatever you do to the water, you're going to do to all the numbers on the line. Let's look at it one more. All right, to wrap us up for today, one Regents question. Here it's a little bit different from the other questions we've been looking at. It's just analyzing table G. The answer here is choice 2. When we look from 10 to 70, and we want the most rapid downward trend, right? Decreases most rapidly from 10 to 70, right? We've got HCl, which decreases not very rapidly. We've got NH3, which plummets down. SO2 with a gentle curve. And KCl, which just goes up. So definitely not KCl. Right, and the only one, right, NH4 doesn't, or NH4Cl doesn't, KCl doesn't, HCl does, SO2 does, but it's not on here. NH3 is our most rapid downward trend. Now, why? Why is that? Why do some of these go down? Why does HCl, SO2, and NH3, why do these trend downwards while everything else trends upwards as the temperature increases? And the reason there is because that these things are actually gases, while everything else here is a solid. And we're going to talk about why that makes a difference next time. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.